Hello students, I am Sudipto Nath, your teacher, and I am back with a new video on kinematics and theory of machines, subject code PCME 503 module 2. And today in this video we are going to discuss about the details of 4-bar mechanism, especially the velocity vector and velocity analysis. And we will try to solve a numerical problem on this 4-bar mechanism relative to velocity vector and velocity analysis. Now over here we see that ABCD is a 4-bar mechanism with the links are AB, BC, CD. All the joints, that is at point A, B, C and D, they are all hinge joints. Now in this type of mechanism, let us consider the prime mover is connected at point A. So AB is considered as crank, BC is connecting rod, CD is the rocker arm, and DA is the fixed link. Now AB rotates with omega 1 angular velocity in the clockwise direction at any instance. So the crank AB has end A fixed and end B rotating in clockwise direction. So the tangential velocity component, or VB, with respect to A, which is actually called as VBA, acts perpendicular to the link AB as shown in figure. Just note, as shown in figure, which I have already shown over here in blue arrow, the velocity vector component VBA is acting perpendicular in the right hand direction, which is analogous to the clockwise rotation of AB. So it is shown VBA. Accordingly, the direction of rotation of link BC, it is in anti-clockwise direction for the inertia of the component. Here, the center of rotation of joint end B. Now we find the tangential velocity component VCB acts perpendicular to link BC, as shown in figure also, with angular velocity omega 2, which is acting in counterclockwise direction. Finally, we get that the link CD rotates in clockwise direction with VCD acts perpendicular to the link CD. Have you got it? At any moment you can pause the video and repeat these things. Okay, so let us proceed forward. Now velocity vector of a 4-bar mechanism, if you are trying to analyze, then if we know that the direction of motion of the 3 vectors, then by knowing directly as a given data or calculated value any one of the magnitude of the vectors, the magnitudes of the other 2 vectors could be found out easily by this relative velocity method. We have to construct the velocity diagram in this case simply by drawing the parallel lines one after the another for this particular vectors. Can you see? In the main diagram, the velocity vector VBA is actually shown as parallel lines in the diagram which is shown at the bottom in triangle form. VCB in the main drawing and in the diagram which is given below, these VCB lines are parallel, as well as VCD lines, they are also parallel. Okay, now the motionless links are concentrated as a single point for any kind of mechanism. Here point A and point D, they are motionless points. So accordingly, the other links are indicated by point B and C, and motionless points are concentrated on a single point which is named as point small a, small d. Now we concentrate on velocity of rubbing. It's a very important phenomena. The rubbing velocity of the 2 surfaces will depend upon the angular velocity of a link relative to the other. Here pin at A, let us consider it as RA, that is radius of the pin at A, and the velocity of rubbing will be RA into omega BA. Similarly, for the pin at D, the radius of the pin at D, that is RD, so velocity of rubbing will be RD into omega CD. Now pin at B and pin at C, what will happen? If we are going to consider, then for pin at B, let us consider the radius of pin at B is equal to small rb. So velocity of rubbing will be rb into omega AB plus omega BC. And same in the same phenomena, pin at C, omega BC equal to omega CB in the counterclockwise direction, and omega DC equal to omega CD in the clockwise direction. So considering the radius of pin, that is RC, velocity of rubbing will be RC into omega BC plus omega DC. So this is only the velocity of rubbing which is required in some situation for calculation purpose and to find out the shelf life or working life of a pin joint or a hinge joint. Now just to tease your brain, look at the figure, look at the given figure. Now try to figure out the tendency of direction of rotation of the link CB. Repeat. Look here, that is A to B, B to C, C to D and D to A. They construct a 4-bar mechanism. Mind it, A to D and B to C, they are actually not touching one another. They are having some gap in between. Now, if the crank AB is rotating in clockwise direction with omega 1 angular velocity and the velocity vector VBA is as shown in figure by blue arrow, then you have to find out the tendency of direction of rotation of the link CB, that is the tendency of rotation of C with respect to B, that is called as the connecting rod. Now try to draw approximately the velocity diagram for the given 4-bar mechanism. Now we are proceeding forward to the numerical problem. So here in a 4-bar mechanism, the dimensions of the links are under that is AB equal to 50 mm, BC equal to 66 mm, CD 56, AD 100 mm, and at any instant when angle DAB equal to 60 degree, the link AB has an angular velocity of 10.5 radian per second in the counterclockwise direction. Then determine number 1, velocity of the point C. Number 2, velocity of the point E on the link BC when BE equal to 40 mm. Number 3, angular velocities of the link BC and CD. Number 4, velocity of an offset point F on the link BC if the length BF equal to 45 mm, CF equal to 30 mm and BCF is read clockwise. Number 5, velocity of an offset point G on the link CD if CG equal to 24 mm, DG equal to 44 mm, DCG is read in clockwise direction. Okay, clear? Now this particular problem which I have collected from the Theory of Machine book by S.S. Ratan. So courtesy goes to Theory of Machine by S.S. Ratan book. So the solution method is as given. The configuration diagram as shown in figure A, where a convenient scale which you have taken, now writing the vector equation velocity with respect to A, that is velocity of C with respect to B plus velocity of B with respect to A. So accordingly the equation, velocity equation is constructed. So this is the velocity diagram finally we have drawn. So taking the vector VBA to a convenient scale in a proper direction and sense as per figure B, VCB is perpendicular to BC. Draw a line perpendicular BC through B. VCD is perpendicular to DC and draw a perpendicular line capital D, capital C through D. The intersection of the two lines locates the point C, small c. Now VCD equal to VBA plus VCB can also be written as VCD plus VBC, that is equal to VBA. So DC plus CB equal to AB as per the vector rule. Now from the given data we know that velocity VBA, that is equal to omega BA plus length AB. Omega BA, that is the angular velocity, which is given as 10.5 radian per second, and the length BA, that is given as 50 millimeter. In terms of meter we can write it down as 0.05 meter. So by multiplying these two we get the VBA value equal to 0.525 meter per second. Next comes the explanation, that is shows the same line joining B and E. The arrowhead should be marked in the other direction so that it represents the vector of velocity B relative to C to satisfy the latter equation. Thus it implies that in case of both the ends of a link are in motion, the arrowhead may be put in either direction or no arrowhead is put at all. This is because every time it is not necessary to write the velocity equation. The velocity equation is helpful only at the initial stage for better comprehension. So the continuation of this thing, we can find out that velocity of C, that is 0.39 meter per second, by measuring using suitable scale. To find out the location of point E on BC, we know that the ratio of the velocity vectors and the actual length will be same or similar. So actual length capital B by capital BC, that should be equal to velocity vector BE, small be, by small bc. So since small bc is measured as 0.34 meter per second from the velocity diagram, so to find out the velocity vector BE length, what we have to do, we have to put the values in the previous equation and we'll get the value as 0.206 meter per second. Because capital BE value is 40 millimeter or 0.04 meter is given, and BC value is 66 millimeter or 0.066 meter is also as given data. Therefore, we are going to get the vector VE, that is equal to 0.415 meter per second. So similarly, we can find out the angular velocity value omega CB and omega CD as 5.15 radian per second in clockwise and 6.96 radian per second for omega CD in anti-clockwise or counterclockwise direction. Next comes to find out the value or location of f, small f. To find out that, accordingly we have to follow the rule of finding out the vector value, and similarly we will get the value of af equal to 0.495 meter per second, and similarly for g, to find out the value of location of g, we can find out the velocity g equal to 0.305 meter per second using suitable scale. So from Vg by Vc, that is dg by dc, over here the actual value of Vg that can be measured or found out. Now omega BA or omega AB in counterclockwise and omega CB or omega BC in clockwise direction, that we know. So velocity of rubbing at point B is equal to RB into omega AB plus omega CB. So RB value is given as 0.040 meter So we can put the values and get the result as 0.626 meter per second. That is the velocity of rubbing at point B. Similarly, velocity of rubbing at point C, that is equal to 0.303 meter per second. In the same way you can find it out. And the velocity of rubbing value at point A and point B, or pin A and pin B, that is found out as 0.315 meter per second and 0.244 meter per second. At any moment you can pause this video, go through this numerical once again. This is very important. Please go through it, repeat it, try to solve it by yourself, get the values. If you are not satisfied, if you have not found out it correctly, or if you have not drawn the velocity vectors, velocity diagram properly by relative velocity method, please do it once again. Please repeat it again and again for the betterment of yourself, for acquiring the confidence, and I hope you can do it and will enjoy it. Thank you very much. We'll meet in the next video and we'll meet very soon. Have a nice day.